Hey guys, welcome back to Mechanical PE Exam Prep. If you'd like to be notified when I post new videos, go ahead and subscribe to this channel if you haven't already. And if you want to get the basics down before solving lots of problems, take my Udemy course, HVAC and Refrigeration Fundamentals. In less than 5 hours, you'll review all the major topics you need for the PE exam. By the end, you'll actually be excited to start studying. Now let's take a look at the next question. What's the humidity ratio of the air leaving the cage room? Well, let's start by thinking about the humidity ratio of the supply air, and then we can figure out how much moisture was added to that based on the latent load. So we know the supply conditions are 82 degrees and 85%. So from that, we can look up in the psych chart what the humidity ratio of the supply air is, and it's 140.8 grains per pound. And let's also look up the specific volume of that supply air, which we're going to need a little bit later. That's 14.1 cubic feet per pound. Okay, so that's what we're starting with. And then there's this moisture being added within the cage room by the latent load, but that's been given to us in BTU per hour. We would really prefer to have that as a mass flow rate of water. What is the actual mass of water that's being added to the air per unit time? How can we get that from the latent load when it's given to us in energy units? This is BTUs per hour. Well, we can use this formula. For the moisture added, we can say that the latent load, Q sub L, equals m dot delta H, where delta H is the latent heat of vaporization, H sub Fg, of water vapor at the particular temperature that we care about. In this case, we can use the conditions of the room, which are approximately the same as the conditions of the leaving air, 87 degrees. So what's the latent heat of vaporization, the energy needed to evaporate water, at T equals 87 degrees? That's a number that we can look up in the steam table, app 23A in the MERM, and then you actually have to interpolate because it's organized by every 2 degrees and it's even degrees, so you can look for 86 and 88 and then take the average, which is easy enough to do. So that will give us this value, and we know the latent load in BTUs per hour is that 18,000. So we can rearrange this, solving for the mass flow rate of water that's being added to the air. It's 18,000 BTUs per hour for the latent load, divided by the latent heat of vaporization from the steam table, which is about 1099 BTU per pound of water. So BTUs cancel, and we get a mass flow rate of 16.38 pounds of water per hour. Now it's arbitrary, but earlier I picked the humidity ratio for the supply air in grains per pound, so I'm going to change this to grains as well. So we'll multiply by 7,000 grains per pound. And we also have the volume flow rate in CFM, so it would be better if this were per minute instead of per hour. So I'm also going to multiply by 1 hour over 60 minutes. So ultimately that mass flow rate of water is going to be 1911 grains per minute. So 1,900 grains per minute of water being added to the air, which already started with a humidity ratio of 140.8 grains per pound. So how do we put that all together and find out the humidity ratio of the leaving air? Well, we can use this formula, which we've used a few times before. The mass flow rate of water equals the mass flow rate of air times the difference between those two humidity ratios, where the leaving air is higher. So I'll write this as humidity ratio of leaving minus humidity ratio of supply. And what do we already know here? We know the supply, because we looked that up based on the supply conditions. We know the mass flow rate of water because we just figured it out based on the latent load. And we don't know the mass flow rate of air, but we do know the volume flow rate of air because we found it in part A. And we know the specific volume of the supply conditions because we looked that up earlier as well. So we know enough to determine that, and the only thing we don't know is the humidity ratio of the leaving air. So we can solve for that. Let's rearrange algebraically first. Humidity ratio of the leaving air, we have to divide by mass flow rate of air on both sides and then add over the humidity ratio of the supply air. So this is m dot water divided by m dot air plus humidity ratio of supply. And now I'll make the substitutions below. 1911 grains per minute, that's our numerator. And the denominator is the mass flow rate of air. So let's use the volume flow rate of air. We found that to be 23,240 cubic feet per minute, and that's a volume flow rate, so we need to divide that by the specific volume, which we found to be 14.1 cubic feet per pound. and that is in parentheses in the denominator. So the cubic feet will cancel, and the minutes will cancel, and we'll end up with grains per pound for that term. And this is pounds of air, plus the starting humidity ratio of the supply air, which we said was 140.8 grains per pound of dry air. And this term doesn't turn out to be very large, so it's not a huge change to the humidity ratio. It ends up being 142 grains per pound, and that's answer B. There is an alternate way to do this as well that might be a bit quicker, although it's tough to be so precise when using graphical methods, but you can just look at the cycle chart and you can draw the process based on the sensible heat ratio. Earlier on, we found the total sensible load and the total latent load. So you can find the sensible heat ratio by dividing 125.5 by the sum of 125.5 and 18. And you'll get a sensible heat ratio of about 0.87. So this would be an alternate method. And then if you're using a version of the cycle chart that has that little protractor thing on the top left, then that tells you the slope of the process line for some combination of sensible and latent heating. So let's suppose state 1 were here. I'm just picking this arbitrarily. Then there's this latent and sensible load in the room, so it would be up and to the right to some point, which we would call state 2. And then you could come down. You know that's going to be located at a point where the temperature is 87. So if you can identify that point based on the temperature and the fact that it has to intersect this line that goes through this point and has that slope, then you can find point 2, and then you just go horizontally over to the right and pick off the corresponding humidity ratio. The reason I don't love this method is because you have to use the protractor, which is a little tricky to be super accurate when drawing these sloped lines. And then the reality is there's only a tiny bit of humidity being added to the air, so the humidity ratio hardly changes. This line itself is almost horizontal. I'd be a little worried about being accurate there. I prefer to work it out algebraically.